Welcome to the 19th chapter of the Crystal Clear Electronics video series. Divided into 3 separate videos, we present the chapter of the curriculum using the EEPROM Non-Volatile memory, written by Szabó. Today's lead speaker is Ádám Szabó, a mechatronics engineer. He has been involved in developing the Crystal Clear Electronics curriculum from the very beginning.
I would also like to welcome everyone to the screen. My assistant is József Domokos, a lecturer at Sapientia University in Romania. You may have already met József in the videos of Chapter 11, where you learned more details about microcontrollers. You have probably heard the term EEPROM, but do you know where it is used? We don't usually think about it in everyday life, but nowadays we are practically surrounded by EEPROMs. For example, here in my immediate environment, I have at least 8 EEPROMs. Let's see what they are. For example, I have an EEPROM in my phone. Can you guess which part I mean? No, not the many gigabytes of memory, but the SIM card in the phone. Or here in my wallet, I have, for example, 2 bank cards and an access card, all with EEPROMs. I have 3 RFID tags in my keyring, all of them contain EEPROMs, and I have this ignition key, which also has EEPROM. They all store some kind of security code, mostly reprogrammable, that can identify you. SIM and bank cards, for example, store not only their identification code, but also a PIN code that we can change.
I haven't even thought about it before. I have a couple of EEPROMs too. Let's get started on the 19th chapter of the curriculum and learn more about EEPROMs. But first, let's look at the different types of memory. There are volatile and non-volatile memories. Volatile memories lose data when the power supply is turned off, while non-volatile memories retain it.
That's true. In the previous chapters, you could already read about some of the volatile and non-volatile memories found in microcontrollers. An example for volatile memories was RAM, or random access memory, which has very fast access speeds and as such perfect for storing variables and results of operations. However, when the supply voltage is turned off, the RAM loses all the information stored inside, so if we were to store our code in RAM, we would have to reprogram the microcontroller after each restart. This is unfeasible in most cases. József, what would you say if every unit in your car stored its program code in RAM?
Well, Ádám, it would be absurd if every time I turn the ignition key, I had to call a car electrician to come out and program the 30-40 microcontrollers in the car. I think what is needed here is a non-volatile memory, in which to store the program code and the information we need to retain.
This is the reason why ROM, or read-only memory, was developed. As you can guess from its name, this memory type was only readable. It was written once during manufacturing with the program code and constants, and you had no way to modify the contents afterwards. You can obviously feel that this was a huge restriction on the users and engineers' side, since this memory chip was only usable for one task. PROMs, or programmable ROMs, gave a little more leeway, as they were programmable by the user to suit the task at hand, albeit only once. However, it had the disadvantage that it was an OTP, or one-time programmable memory, so if you made a mistake, the chip had to be discarded.
Yes, for example, if you wrote a wrong instruction in your program, say you accidentally wrote -b instead of +b, or made some other mistakes you didn't notice before writing the memory, then all the memory went to waste. Or, if we wanted to modify our code later to add a new function, we would have needed a new memory unit since we could not change the contents of the existing memory. Think of it as if you had to buy a new backup drive for your computer every time you install a new software.
The PROM was followed in development by the EEPROM, erasable programmable ROM, where you had the ability to erase the chip's contents by UV light. This gave users a much greater freedom, but to erase the chip, you needed some special equipment, a UV light source, which was still a restriction. Finally, EEPROMs, electronically erasable PROMs, brought the real breakthrough, as they could be programmed and erased electronically. Although this upgraded non-volatile memory has the term ROM in its name, there are only historical reasons behind this. We can not only read, but also write and erase them.
At this point, I would like to note that writing is an operation where groups of data in memory, in this case bytes, are set to arbitrary values. An erase is a special write where the data bits are filled with either all ones or all zeros, depending on the type of memory.
With EEPROM, we have a memory that we can use to store data or program code that we will need after reset. Unfortunately, this property has a negative impact on performance. The speed of EEPROMs is much lower than RAMs. For example, in an Atmega 16A, reading and writing RAM takes only 2 clock cycles, which is 0.25 microseconds, with an 8 MHz clock, whereas doing the same with an EEPROM takes 8.5 milliseconds, which is 34,000 times slower. You can imagine this as short-term and long-term memory in humans, which means we can remember things fast, but to retain them for a long time, we need a longer time to process it. Another non-volatile memory type is called flash memory, which is an improvement over the EEPROM, where the aim was to increase data density and thus reduce costs. It was achieved by implementing the erase subcircuits not for each byte, but in larger groups called blocks. This way, a single byte can be deleted only if you copy the whole block to somewhere else, erase it, and then copy everything back, leaving the deleted byte out. This is obviously slower than deleting one byte on an EEPROM. In common flash memories today, when reading and writing, we have access to a whole block instead of a byte, so in that case, it is faster than an EEPROM. You can probably see from this that flash memory was not designed to access or clear single bytes, but to access big chunks of data, so it is best to write the whole program code into the memory, and when starting the microcontroller up, copy everything to the much faster RAM. EEPROM, on the other hand, makes it easy to access a single value, making it perfect for storing parameters, calibration constants needed by our program. These memories and EEPROMs have a finite lifetime, unlike RAM, which is usually given by the manufacturer in the guaranteed number of writes and erases. This write-erase cycle count is usually higher in EEPROMs compared to flash memory. For example, in the Atmega 16A microcontroller, the flash is guaranteed to withstand 10,000 cycles, while the EEPROM is guaranteed 100,000 write-erase cycles. This means that we can modify each bit of the memory region that many times.
We've discussed the origin of the term EEPROM, but do you know what flash memory was named after? One of the rumors is that the simultaneous erasure of data reminded its Japanese inventor of camera flashes. The other rumor is that the promoters wanted to find a short but catchy name for this memory to emphasize its speed over EEPROM and give their product a market advantage. So they chose the name Flash. The third story is that the engineers were reminded of block erasure, like when they shone a high-intensity UV light on the EEPROM memory and erased everything at once. That's why the term flash spread. We don't know exactly what the truth was. Which do you think is the most likely explanation?
Let's continue with the possible uses of EEPROM memory, some of which we already showed you at the beginning of the video. During certain tasks, we need a parameter in memory that retains its value after turning off the controller. If you want to be able to modify this value at runtime as well, it's not possible to store it as a constant in program code. A constant does retain its value after reset, but it cannot be changed. A variable's value can be changed, but it doesn't retain its value after reset. A great solution would be if we could modify the code itself at runtime, and thus the value of the constants inside it. This, however, causes some problems, as the deterministic behavior of our program could be compromised. We could accidentally modify something that could change the behavior of our program. We could define a region in memory instead that is exclusively used to store parameters. This can be done in two ways, either by hardware separation or by software separation. The former means that some part of the flash memory is accessible at runtime, but the rest of it is not. It can also happen that the microcontroller allows access to the whole flash memory. In this case, it is the job of the software developer to separate a region in flash to be used. In the Atmega 16A, the latter is true. The whole flash memory can be modified at runtime, and it is extended with a 512-byte long EEPROM. If the microcontroller has a dedicated EEPROM, such as the Atmega 16A, it is usually better to use that instead of the flash, as its lifetime is an order of magnitude longer.
Ádám, this theoretical background is very useful, but I think the viewers would also like to know what exactly these memories can be used for and where they are used.
This is a very important topic. EEPROM is usually used to store configuration parameters that are required for correct operation, parameters that the end user can modify freely, or logs that record the activity of a device. For example, a remote control of an AC unit can store the last temperature set in EEPROM, which would be frustrating to set again every time you turn on the AC. Or, if we are writing software where the speed setting of the serial port can be changed, and we can't or don't want to change this setting at every startup. In this case, we can simply store the setting in EEPROM. In industrial applications where it is important to record any abnormal behavior, the device can store an error code in its EEPROM, so the reason of failure can be identified when servicing, similarly to the black box of an airplane.
For example, when I take my car to a mechanic, they read out the fault codes stored since my last visit and the recorded mileage.
EEPROMs can also be used to retain calibration information of sensors. A good example would be a joystick or steering wheel controller connected to the PC, because when plugging it in the first time, we have to calibrate the maximum range values in each direction, and later the device remembers. If you wish, you can recalibrate with new values. Or, for example, in a weather station, it could be important to save every day the lowest and highest temperature of the day, or the highest wind speed, and we don't want to lose this accurately measured data if the power goes out. We can store user settings, such as the parameters of the motor in a motor controller, coil resistance, inductance, maximum current, speed, power, control parameters. This way, we don't have to program these values over and over again after each startup, but when connecting the controller to another motor, we can modify the parameters quickly, even with the values measured with our own motor controller.
An access control system could store the identifier in the EEPROM of the user's device, and the wall unit can store the entries made by each user and the date of the latest entry and maybe even the number of failed authentications.
Monitors also have an EEPROM, from which the computer reads out the manufacturer, model, supported resolutions and refresh rate, and the monitor stores display settings such as brightness, contrast and color balance.
This brings us to the end of the first video of chapter 19. Thank you for joining us. In the following video, we will show you the life expectancy of EEPROM memories and some solutions to extend it. Stay tuned for the next video. Bye!
Bye.